monitor, and then please introduce yourself, say hello to the students. Thank you.
Dan Chuan-Zhou from Taichung Donghai Dashi.
谢立从中正大学。
Hello, I'm Lu Zhenliang from Kaohsiung Senior High School.
Yes, thank you. And then are you yourself?
So we're all-nighter from the Taipei American School, and then I'm Hyunwoo Chun, Justin Wen, Alex Do, Kenneth Mo, Shirley Lee. Thank you.
We're Junior Cole from 建国高中，还有张雅晨、徐德仲、陈以俊、赖志荣、杨佑宇。
Hello, we're Team Animation from Legal Junior High School, and my name is Lee Yuan, 谢浩君、洪伟翔、林明慧、吴胜。
Then I think now everybody's here. We are going to start our presentation. Then okay. Then please change the topic from the opponent.
We would like to challenge number 14, Bola memory.
Number 14.
Yeah, 14, Bola memory.
Yes, we have 7.
This one.
Honorable judges and worthy opponents, I'm a reporter from Team Detonation. So today I'll report the problem for team bond membrane. So this is our outline. So this is the problem statement. So we need a metal ball and a rubber membrane and a plastic cup. And our aim is to find the origin of the sound and its characteristics depend on relevant parameters. So our focus today will be 2 points. For the first one, the origin of the sound, and the second one is the characteristics of the sound. So first we want to discover the origin of the sound. So here's our theory for the origin of the sound. We believe when the ball falls onto the membrane and when it leaves, it causes the membrane to have vibration. And the vibration of the membrane causes the vibration of the air molecules around it. So as you can see in the picture, the blue dots on the picture refers to the medium for transporting sound waves, and the membrane will have resonance. And the air molecules inside the cup will amplify the sound. So to verify if our theory is the correct one, we do the experiment with different height of the air column. So as you can see, we have 6 different height of the air column for our experiment. So before we start our experiment, we wanted to check out the natural frequency of the container, because if the vibration frequency fits the frequency of the container, it will amplify because of resonance. So as you can see, here's our result. So we use a frequency generator to create a spectrum of different frequency of the sound, and you see at what certain point does the sound be amplified because of the resonance of the cup. So as you can see, it's about 265. So here's our result for different height of the air column. As you can see in the result, with different height of the air column, the lowest frequency, which is the fundamental frequency, nearly refers to the same number. As you can see, for example, for 9 centimeter, it's about 250, and for the other height, it nearly is the same. And here's also a point I want to point out is that the fundamental frequency here is the highest because we believe it might, because it fits the natural frequency of the container, as I previously stated. So now we find the origin of the sound. So first, sound is a pressure wave created by a vibrating object. Second, the medium, in our case, is the vibrating membrane, transport the energy to the particles in the surroundings area and in the air column. So in our case, it's the air molecules. And for the third one, resonance amplifies the amplitude of a certain frequency that corresponds to the natural frequency of the container. So now we'll move on to a theory, which is different characteristics be influenced by different parameters. So first we want to explain the vibration mode, and we use the Basel function. So with the Basel function, when we plug in the number of circular node and linear node into it, and we put the function into a computer program, we can get the following numbers. This is the resolution for Basel function. And so for example, if we have one linear mode here and one circular mode here, we get 3.832. Here's what we get from the program, and we can see with different vibration mode, they have different shapes and different frequencies. And here's the certain frequency and the ratio between each frequencies you can see on the chart. For example, 1.1 mode is 1.59 the times of the fundamental frequency. So later on, I'll elaborate on some of the frequency we detect in our experiment. So first one is the fundamental frequency, which we call 0.1. So it has the lowest frequency. Here's the second mode, which we call 1.1 mode. And because of the shape, as you can see on the picture, it forces the air back and forth. Therefore, it takes much less energy than the previous mode. Third one is the 2.1 mode. It is less efficient at radiating sound energy than the 1.1 mode because of the X shape. And for the fourth mode, it is called 0.2 mode. It has one nodal diameter, and it decays faster than the previous 3 nodes. So we theorize that it might be hard for us to detect this mode in our experiment. Now move on to our experiment results and analyses. So first, to accomplish our experiment, we need the following equipment. So first, we draw a scale with equidistant markings on it, so that on the latex globe, so that we can create proportional tension of it. So second, we use level to make sure the cup and the membrane is horizontal and leveled, so that every time the ball falls onto it, will always fall onto the center of it. And third, we use electromagnet and switch to make sure when the ball falls, we do not add additional force onto the ball, so that we will not let the ball spin, so the energy will not be taken away by the spinning of the ball. And last, we use our microphone. In our case, it's the condenser microphone to detect the result of our experiment. Here's our overall experimental setup, and I want to put up a point is that we do 10 experiments for each condition and calculate the average and take it into our data set. Here's what we do before each experiment. So we detect the surrounding noise, because it might influence the result of our analysis. So as here you can see, this is the surrounding noise, and the frequency here is about 150. So move on to the next graph. You can see here's our normal experimental result, and the frequency here is about 150. So we refer to it as the surrounding noise, not the sound created by the membrane. So in our analysis, we do not take the little peak into our consideration. Now move on to different parameters influences for the result. So first, we want to discover how varied mass of the metal ball will influence the sound. So in our experiment, we have 7 balls, and now it's our explanation of the energy transformation in the system. So before the ball falls, it has the gravitational potential energy in the system. And when it falls, then it turns into kinetic energy and it accelerates. And when the ball finally falls onto the membrane, the energy transfers into elastic potential energy and sound energy. And for this experiment, which is different masses of the ball, we theorize that the elastic potential energy may be bigger and sound energy remains the same when we have bigger ball. So here's the result of our experiment. We can see with different radius of the ball, which means different mass of the ball, the frequency nearly remains the same. So it fits our theory that the sound energy, which is the frequency of the membrane, doesn't change. Here we also divide each frequency by the fundamental frequency. As I previously stated, based on Basel function, it has a certain ratio between each frequency. So as you can see, the 1-1 mode and the ratio between the 1-1 mode and 0-1 mode is about 1.59. So it also proves that our circumstances fits our theory of the vibration mode of the membrane. Here's what we detect for the volume with different sizes of the ball. As you can see, the mass is bigger, then the volume becomes louder. For example, this is the radius of the ball, which is 8 millimeter and 6 millimeter. So you can see the amplitude here is bigger than the smaller ball. So our second experiment is to explore if different height where the balls release will influence the experiment result. So here's the same theory, and we believe that elastic potential energy will become louder and sound energy refers to the same when we have different height. So here's the result. We can see the height does not quite exactly influence the frequency. And also we divide frequency by the fundamental frequency and get a ratio which fits the vibration mode of the membrane. Here's the result for the volume, and we can see when the height is higher, the volume becomes higher. So here's the fundamental frequency formula, and this is an empirical formula. So by this, we can calculate the fundamental frequency of the membrane. So after calculation, we get the fundamental frequency is proportional to the root of the change in area over the area minus the change in area. So this will be used in our further analyses. Here we do our third experiment, which is the tension of the membrane. In this experiment, we vary the level to which the rubber membrane is stretched. Here's the result. We can see when the scale on the membrane is bigger, then the frequency becomes lower. To put it in other words, when the tension is bigger, then the frequency becomes higher. And here we also divide each frequency by the fundamental frequency and get the same result. Here's our analyses, and we can see this is our calculation before, and our experiment dots nearly fits the theoretical line so that the empirical formula fits our theory. Here's our how we deal with the background noise. So the little bit here is same as the little bit here. So we do not take it into our consideration. Here's some other spectrum. So lastly, after we understand how the ball and the membrane will influence the result of the vibration and the sound, we want to discover if we have the same condition of the membrane and the ball, will it affect when we have different material of the membrane? So we do the experiment. We use two different materials. The first one is the latex globes, and the second one is the balloon. So as you can see in the picture, when we stretch the membrane to the same scale, which is number 7, the frequency does not turn out to be the same. In this case, the balloon is higher. So we suppose it might be the difference in tension and density that causes the difference of their frequency. So here's the result of different membrane, and we can see the ratio between the results are both the ratio of 1.4. So in physical theory, that the different fundamental frequency is attributed to different tension and density. Now it's our summary and conclusion. So for the sound and vibration, the sound is originated from the vibration of the membrane, which caused the pressure of the air molecules around the cup. And for the parameters we do in our experiment, the size of the metal ball and the height where the ball is released does influence the volume, but does not influence the frequency. And second, the square of tension is proportional to the frequency of the sound. And third, with different material of the membrane, we get different frequency for our experiment. And now it's our references for the experiment. Thanks for listening. This is at the end of my report.
Did you calculate the tension?
We didn't calculate the exact number of the tension.
Did you change cup diameter?
Cup diameter?
Yes.
We didn't change the cup diameter.
Thank you. Did you test amplitude?
Amplitude of the sound? Yes, we do. And we can see it from the picture of the spectrum. Thank you.
Did you change the, did your cup deform?
What do you mean?
Is it a rigid structure?
Or rigid?
When you
Membrane?
bounce the ball on the membrane, is it, does it deform?
The membrane deforms?
No, the cup.
We consider the cup do not deform.
Okay, thank you. Did you drop your ball at the same height for each trial?
As I said in an experiment, one parameter is different height of the ball. So in that case,
Thank you. Did you try to drop the ball at different locations on the membrane to explore the characteristics of sound?
yes, and we believe that the vibration mode will not be the same.
Okay.
So in our experiment, we
Thank you. Did you observe different frequencies of other than the fundamental frequency?
yes, we do. We do observe the overtone frequency, as I briefly stated in my
Thank you. Did you always observe the fundamental in every trial?
yes, we do.
Okay, thank you. Is your mass density the same when you stretch it?
Mass density on the membrane?
Yes.
No.
Okay, thank you. Does your cup vibrate due to the dropping of the ball on the membrane?
Yes, it does.
Okay.
And because of this, it may cause
Thank you.
the amplitude becomes louder.
Thank you. How do you ensure your tension is constant throughout all your trials?
We make sure this by when we do our experiments, we contain our experiments within 15 minutes, and
Thank
if we
you.
change to another, thank you.
Can you move on? Okay, thank
Okay.
you. Did you find a correlation between tension and mass density?
Yes, we do. Thank you.
Thank you.
noise empirical model.
Today I'm the opponent for the problem 14, the ball membrane. So essentially, when dropping the ball on the membrane, the problem statement is what it is currently, and so our ideal structure for solving the problem is first determining the origin of the sound, then by determining the membrane properties, forces acting on the membrane, then next to analyze the unique vibrations of the membrane, and by looking for membrane modes and theory accountability, then we investigate the phenomenon under different parameters, to include initial drop conditions and other parameters. So some pros and cons to the report. I thought that what was really good was that there were clear phenomena footage. They tested multiple relevant parameters with comparison, and they have comparison between theoretical and experimental results. And they also considered many initial experimental conditions. And some cons were that the reporter did not account for the oxidization of rubber over time, and they are lacking analysis of certain characteristics of sound in relation to parameters. They are also lacking theory limits. There's no axis label, and they do not explain the correlation between the graphs. They also assume tension is constant throughout, which is clearly not true, and they did not explain a way to find the modes. And they also refer the theoretical equation as an empirical formula. However, formulas cannot be empirical because empirical suggests that it's found by experiments. So the points of discussion that I would like to make include parameters, the things of varying tension, the drop height, varying drop height, ball mass, changing the volume of the cup, changing the diameter of the cup, and the initial drop conditions and drop locations. And for experimental setup, I would like to mention maintaining the same tension and the unequal mass density distributed throughout the membrane, and the dropping of the ball and cup conditions. And for experiments and analysis, I would like to talk about observed peaks, theoretical and experimental models, parameter correlation with characteristics of sound. And for theory, I would like to talk about tension and mass density relationship, the correlation between cup volume, drop height, and amplitude, and the calculation of tension. I would like to start my discussion time. Thank you. And first, I would like to ask some last clarifying questions from before that I could not finish. Would that be okay?
Okay.
Thank you. Did you observe frequencies that were lower than the fundamental frequency?
We do observe the frequency lower than fundamental frequency, and we do know that's the sound from the surrounding, so we take it out of our consideration.
Okay, so like there are lower frequencies.
From the surroundings. That's noise.
Okay. Could I see like experimental data for what you just said?
Okay. Yes, this one. So as you can see, here's the fundamental frequency we suppose, and this one is the noise from the surroundings, and it fits what we detect from the surrounding noise when we do not let the ball falls onto the membrane. So we can reasonably take it out of our consideration.
Okay, so you're saying that the fundamental frequency is around 225?
Here is about 250, more or less.
Okay, and so the sort of like the smaller, the peaks that are less than the fundamental frequency is around 100 and...
150? Yeah.
Okay. So, have you considered that there are things called subharmonics?
Can you rephrase it?
So I can draw. So, for example, when there's a membrane and there's a cup underneath it, you see that the membrane is vibrating.
Yeah.
And that the cup also vibrates.
Yes, and that's caused the higher amplitude of the frequency because of resonance.
Yes, I agree on that.
Thank you.
And also, but like, have you considered that there are times when the cup does not vibrate at the same frequency as the membrane?
We believe the cup vibrates at the natural frequency of the plastic cup, and that's the certain frequency that will cause the certain amplitude of the frequency to become louder.
Okay, but then so there is like, so for the volume, I believe that there are also times when the cup could vibrate at a frequency that is perhaps lower than the membrane vibration, and I believe that by doing so, it creates something called subharmonics. Like, some research papers have mentioned that there are things like subharmonics that are exciting. That subharmonics mean they are frequencies that are lower than the fundamental frequency. So, what do you think about that?
I believe that might be a possibility that will influence the result. And for that point, I believe that might be an improvement in the future. However, our point in this experiment is that the resonance of the cup can cause a higher amplitude of certain metals.
However, I believe that the problem statement says to investigate the origin of sound.
Yes, and I have discussed it before. That comes from the vibration of the membrane.
Yes, I agree. But for the part about subharmonics, I think that I would suggest that perhaps in future considerations, you could take into account the vibrations of, other than just eliminating it as potential, as just surrounding noise, ambient noise, you could perhaps consider that the vibration could.
Yeah, I think that's one of the improvement I can do in the future.
Yes, thank you.
Thank you.
And so for moving on to an equal mass density, I was thinking that can I see the slide on your experimental setup, like how you
What experiment exactly?
like dropping the ball, like when just any
Okay, this one is okay.
So how exactly did you tie the membrane on the top?
We used a rubber band and we stretch the membrane to the certain scale on it. So we can create a certain tension, or we can cause a proportional tension when our parameter is different tension in our experiment.
Have you considered that over time, the membrane could possibly go upwards, like when the rubber is not exactly secure, correct?
I think that's true. So in our experiment, we want to minimize the influence of this problem. So we do our experiments within 15 minutes for each time.
Okay, that's really good. But also, have you considered that there is oxidization of rubber over time?
I think that might be a possibility that will influence it.
Okay. And so, when you stretch the membrane, how do you stretch it?
We pull it exactly. We pull it at every side and just make it to the perfect scale that fits our experiment setup.
Okay, but it's quite impossible for you to maintain the same tension for each direction when you stretch the membrane of the cup.
Why not? We use the scale to minimize the influence. So we believe that's not a problem in our experiment. Or maybe you can rephrase it.
So I feel like, so you know how like when you stretch something, it's like this. You can't equally distribute the tension over.
Yeah, I see. I just said that we pull the membrane at every side so that each time I do not do it myself, we have teammates, so we put it together so that can minimize the influence of it.
But however, the opponent believes that it could possibly be also contributing to errors.
Yes, and I think because that's a rubber we use the rubber band, so it causes the circular force. So maybe will not have the problem you have stated.
Could you clarify what you mean by that?
I said we use the rubber membrane on the side of the membrane that is secure. So I believe that causes the circular force. That may not be the problem you have mentioned.
So I was saying that when you stretch it, it's quite impossible you could maintain tension for each direction to be exactly the same.
Yeah,
You recognize this as a problem.
we believe
Potential.
that's a potential small problem, so we can just ignore it because with the rubber band it creates circular force, and so the membrane is evenly distributed.
So moving on to the next part, have you considered changing the diameter of the cup?
We didn't take that into consideration.
According to your theory, which is F equals 0.766
Yes,
times
that's
square root of T over sigma divided by
Yes.
E. Do you agree that increasing the diameter of the cup could potentially change it?
According to the formula of F equals to 0.766 and the root of tension over density and over the radius, of course, it will. And I think that might be a possible influence, and it depends on different circumstances.
Okay. So I suggest that perhaps in future experimentation, you could take the diameter of the cup into consideration.
Okay, thank you. That might be a probable improvement in our future.
Okay. And was there a way, for theory, was there a way where you calculated tension? Because I saw in your graph that you had tension.
There's a way to calculate the tension, and we can, so that this is the setup for the experiment, and we stretch the membrane here, and here. This is a theoretical model of the experiment, because for the membrane, it's too hard for us to detect the exact tension of the membrane. So we come up with this way to do the experiment. So this is the membrane, and because the low point here is small, so we can consider it as a ideal long tube. And when we add some mass here, it will stretch the membrane. And to see where how much the scale is stretched, we can calculate what tension is there.
How exactly?
So because different masses will cause different stretch of the membrane. So we can calculate this, and we can get the relationship between the mass and the lines that the membrane is stretched to, and we can take it into our consideration for the membrane line.
Okay. So I think that there's a way that I suggest you could find the tension. So for example, suppose that this is a ball. Oh wait, no, this is too big one. Let's move over this. So suppose this is a ball. And this horizontal line is a membrane. And then this part over here, so here, delta y will be the displacement of the membrane, and theta here, and then the r would be the radius of the membrane. So since change in y is vertical displacement and r is radius, we can say that T, which is tension, force, times 2 pi r tangent theta equals mg. And T times 2 pi r would then become change in y, this, and 2 pi r times change in y over r equals mg. And then you would get a formula for tension, which would be T equals mg over 2 pi. So I believe that by using this tension, by using this calculation, you don't have to, oh, sorry, could I please?
Okay.
Thank you. So for this, okay.
Thank you. That's a great discussion.
Yeah. So for my summary, today we discussed the phenomenon, which include the fundamental frequency and also subharmonics, which included cup vibration and the membrane vibration, and there was and frequency was also And also the presence of subharmonics where frequency was less than the natural frequency, and provided a suggestion for him to account for that. And for experiments, I talked about membrane setup, the stretch, and that the membrane can go upwards since the rubber cannot sufficiently secure it, and that there's oxidization of a rubber, and it cannot maintain equal tension, which is not constant. The reporter says circular force from the rubber band. However, that wasn't really clear when I clarified that. And changing the diameter of the cup was a suggestion that I also presented for them, and that I also suggested a way to calculate tension in terms of setup. Yeah, thank you.
Okay, for the reporter, can you have you confirmed the origin of the sound? Namely, have you tried like putting a membrane on a ring? Does it still have a sound?
It still has the sound.
It still has a sound?
Yeah.
Okay, can you go to page number 7?
Here's page number 7.
You said that the frequency of the container has amplified the sound, right?
Yes.
Can you explain why and how?
Because in this little experiment, we used the frequency generator to cause the sound from a very little to really large, and we put the cup beside it. So if it has some resonance and that amplifies the sound, we can detect it from our microphone and our program for it.
So the natural frequency of the container matches the natural frequency of the membrane? So that amplifies the sound?
In our theory, that is the case.
We have calculated that the membrane has the same natural frequency, and you can find exactly the same frequency for the container.
Exactly, we do not calculate the exact number for it. We observe it in our experiment.
Okay. Okay. So in your experiment, you only showed 4. You calculate like 4 ratios between the frequencies to confirm that the Bessel function actually works.
Yeah, we do the calculation for it.
But there are other peaks. So does the other peaks match the Bessel function calculated?
Maybe you have a misunderstanding for my calculation. So this is this is the fundamental frequency, and this is the 1 mode, which is the overtone frequency, the first overtone frequency. So the ratio between this frequency and this frequency becomes about 1.6, and that's our calculation for the experiment, and that fits the Bessel function theory.
Yes, but I mean other peaks. Do they match the Bessel function? Have you calculated the ratio between this and that?
We calculate these things because we believe the sound is from the ball falls onto the membrane. So we do not consider these down because of the surrounding noise.
Okay, thank you. For the opponent, you mentioned unequal tension in the membrane. What effects do you think it has?
So I feel like in the slide where he included the modes,
Yes.
The unequal tension could possibly, like even when you drop the ball in the middle, it should supposedly, the other side, yeah, this one. So I think it should supposedly, theoretically, it should hit 01, 02, and 06.
Okay.
And then, but then with the unequal mass density, it's possible that it could excite modes 1-1.
Okay, so it excites different modes.
Yes.
Lastly, have you considered the different frequency spectrum at different times? When did you measure?
Times?
Yes. Did you measure? When did you measure your frequency spectrum?
Over the whole process.
Okay. Thank you. I'm the reviewer from Team Miracle. I'm going to be reviewing bond membrane. So this is our focus. We believe we should investigate the origin of the sound, the relevant parameters, and how they affect characteristics of sound. For the reporter, he demonstrated the sound after it hits the membrane. For their theory, they explained by using the vibration of the membrane and the Bessel function. For the experiment, they changed the mass of the ball, the height, and the tension of the membrane. For the pros, they had a clear demonstration of the phenomenon. They had a well-controlled experimental setup. They considered a variety of parameters, and they had good time management. However, they did not have a theoretical explanation for the effect of air column. They did not confirm the origin of the sound experimentally when they were presenting, and they changed the mass and the size of the ball at the same time. For the opponent, she had a good summarization of the report. She discussed possible sources of error, such as tension variation and subharmonics. For her pros, she gave structure to the discussion. She had detailed evaluation, and she brought in many points. However, she missed the effects of resonance of the cup and focused on subharmonics only. For the discussion, the opponent asked, did you observe the frequency that were lower from the fundamental frequency? The reporter said, yes, we think those are caused by environmental noise. The reviewer thinks that the noise may not just be fundamental noise. It may also be internal noise of the microphone. Also, we think of, yes, and for the opponent, she asked, do you think the vibration of the cup introduces new frequencies? The reporter said, we think the vibration of the cup resonates generated by the membrane. The reviewer said, thinks that the subharmonics might be a possible factor, but the noise is also, yes, okay. For the next discussion topic, the opponent asked, have you considered the diameter of the cup? The reporter said, we didn't take that into consideration. And the reviewer agrees with the opponent that the reporter should verify his theory by varying the diameter of the cup. For the next discussion topic, the opponent discussed how the reporter measured tension. The reporter said they added mass and stretched it. The reviewer thinks that the measurement setup is different from the actual setup, so there may be variations between the actual tension and the measured tension. Lastly, this is the points missed. First, they missed the discussion of energy decay of different modes. So many modes have different energy decay rate. So different measurements at different points in time might have different frequency spectrums. Secondly, how the frequency spectrum changes, which is what I just talked about. Thirdly, they dismiss any frequency they consider noise. So they did not remove noise directly from their frequency spectrum. So maybe if they removed it directly from their frequency spectrum, they will find that at the noise peaks, there will also be some amplitude at that frequency. Fourthly, they had no theoretical confirmation for their fundamental frequency. And lastly, they changed the mass and the size of the ball at the same time, so they cannot confirm the effect of mass or ball, or the mass.
Honorable judges and worthy opponents, and now I will start my concluding remarks and some of the explanation in our experiment. So the first question is about the origin of the sound. So we believe the sound is caused by the pressure wave on the membrane. And second, the resonance amplification causes the louder sound. So here's the third point we discussed before, which is the way to deal with tension. We think that might be a possibility to improve in the future. However, I think there's a little more points to consider. Like, I believe maybe because the ball has their contacting points, so the angle here should not be a straight line. So it has a curve. So I believe that might be a possible improvement for both of us. And here's our possible improvement in the future. So first, we may consider the diameter of the cup to explore if it will influence the fundamental frequency or the amplitude. And this is considered in our formula, and we believe it will. And second, we may take the vibration of the cup into consideration, and we believe this will cause certain frequency to become louder, as I stated. And we may have the exact calculation of the tension, which is just I stated here, and here's some correction with what we may have in the future. And there's another point I have to clarify, because we believe the ball falls on the membrane, and when it leaves, it causes the vibration. So whether the size of the ball is if it's big or small, the contacted points does not influence the sound. So it just influences the tension. So we believe the problem that we review a state doesn't have a great influence on the experiment. And last, the span of the observation of an experiment is the whole span of the bumping of the balls. So we can detect all of the frequencies. Thank you.
Thank you. Yes, please.
I have a question for 3 teams, so please just tell me the answer. Don't explain your reasoning. In your experiment, I think you didn't study the variation of impact position of the ball. Is that right?
That's right.
Okay. Do you think the change of impact position of the ball to the membrane will change the fundamental frequency or not?
I believe it will change the mode.
Yes or no?
I believe it will change the mode.
Yes. Your answer is yes. No.
Yes.
Okay. I'm done.
Yes, please.
Okay, would you please turn to the page 14.1 or 43?
43.
Yeah.
Here's the page.
Yeah. Okay. So as the opponent and the reviewer mentioned about your experimental data, yeah. Would you please tell me about for your equation to calculate the frequency of, for example, the vibration mode for 1 to 6. That's what's the ratio of the vibration mode versus the frequency.
Yeah, and the ratio we get is from the Basel function, and the resolution of the Basel function.
I don't think that relates to just the most fundamental frequency equation. Would you please tell me how can you get
comparing the amplitude?
Amplitude. We think it's
sorry. Or you just tell me what's the ratio between the, for example, the mode 5 and the mode 1. What's the relationship between the data?
Can I check the answer?
Yeah.
Check the question?
Yeah.
Are you asking the relationship with this point and this point?
Yeah.
Because based on the Basel function, the different modes have different ratio between them.
Yeah. So what's the ratio?
Can I turn to the previous pages?
It's okay. Yeah. Would you please tell me the opponent? Would you tell me about what's the theoretical explanation of the experimental data?
So do you mean the reason why they are different?
Yeah. Based on the theory. It's okay, or the review.
I think they have different vibration modes, so they will have different ratios between mode 5 and mode 1.
Yeah.
Yeah.
So you think that's reasonable for the ratio of the different mode?
Is that reasonable?
Yeah.
I think they have to calculate the Bessel function theoretically to determine whether that ratio is reasonable.
Yeah. So in your opinion, do you think that's reasonable, or what's the something wrong with your opinion? It's okay. Or any? Do you want to tell me something more?
I believe the different frequency is caused by the different modes because they do have different frequencies. So our theory is just I said, the Basel function, and the Basel function solution can come to a certain number for each frequencies. And with that number,
It's okay.
I have the question that when you measure the mode 1, mode 2, mode 3, mode 4, mode 5, they are measured simultaneously, right?
yes.
Sorry, can I clarify your question from before?
Okay.
Sorry, because I thought you were asking about modes, but I believe that the fundamental does not change. I was just talking about the frequencies created, because the modes change, but then the fundamental.
Okay. Follow the question. Since the problem is that since that's the case, you drop the ball at the center, right? Would that be the difference when the ball dropped not in the center but in the different position?
Yeah, I believe that will influence the result because, for example,
Okay, let's see.
okay, thank you.
I still have one comment. I will give my comment to the reporter. You give a very excellent presentation, but if you have done one thing that will make your report more perfect, is that demonstrate how do you do the experiment.
I see.
You did not show how did you do the experiment, and you just jump to the data and discuss the data. Okay?
Yeah, I'll improve it by.
No, that's it.
Thank you.
Good. Time's up. Thank you very much.
That's a good discussion.
Thank you everyone. And then now for learning.
You shouldn't say anything. You shouldn't say, Coach cannot interrupt discussion. Coach cannot talk.
Everyone's ready? Then now this one. Go ahead. From the reporter. There are 6, 8, 8, 7, 9.
Thank you.
Then for the opponent, 7, 7, 9, 9, 7. Okay, now for the reviewer, 7, 9, 9, 8, 8. Thank you.